So, hi everyone, I'm Janmajaya and I. Hello? Am I audible? Okay. I'm Janmajaya and I work at Privacy and Scaling Exploration Group at EF. And today I'll be talking about Scale, which is a way to offchain microtransactions. But throughout the presentation, I'll be going through what are the different ways of performing microtransactions today and then how we can improve it further. So, what are microtransactions? You can think of microtransactions as small transactions which are not feasible to put on chain directly. You can sort of aggregate them off chain and then put them on chain because they're not feasible to compete for the block space. So for example, you would want to pay a person, let's say $1 every 10 seconds. So it isn't feasible to actually put that on chain because even in a very optimistic case, it might be like the transaction fee on a roll-up would be like, let's say 5 cents. And if you pay them over time, it wouldn't be good for you. It would be really expensive for you. So, and in most cases, microtransactions are paid in higher frequency. So you can sort of imagine that you pay per second or per minute or per 5 minute. So you wouldn't want to actually do that on-chain directly, which is why you need off-chain transactions. So I'm here talking about microtransactions, but why do you need them? So one of the very futuristic applications that at least I have in mind and people at PSC have in mind is the mesh network. So you can sort of imagine a mesh network as a network of hotspots that actually extend your current network. So for example, it extends the internet to remote places where you got hotspots, and then those hotspots are paid for every byte that they route. So you can sort of imagine paying them a cent for a byte or less than that as well. So without microtransaction, this wouldn't be possible. You can sort of imagine turning IPFS, which is an open source product by Filecoin, into a CDN, so where you actually get paid for per byte of data that they transfer. You already have existing applications like LivePeer, the Graph, and in Graph you can sort of imagine that. I'm not sure whether they're doing it right now, but in the decentralized indexer network, you can imagine that you pay per query, right? So you could have things like that with microtransactions. You've got Orchard Network, which is a P2P VPN, where you can right now you can check it out that it's per byte. So they actually pay per byte of data that is routed through the nodes. And then you can also sort of transform the way you actually pay online. You can sort of pay per second for live shows or podcasts. So what are the ideal properties that a particular microtransaction system should have? And I believe that these are the ones. So it should be off-chain. As I said before, your microtransactions should be competing for block space because that will be very expensive for you. It should be secure. So what do I mean by secure? Let's say you're doing off-chain transactions, but what if you're not able to redeem it for value on-chain? So there should be a guarantee that the off-chain transactions, the value underneath every receipt or whatever you're exchanging off-chain, should be redeemable on-chain. You should not require setup for every new interaction that you do. So for example, you've got A and B, and A is paying B in microtransactions. You don't want that when A wants to pay C in microtransactions, they will have to interact on-chain. Because, okay, fine, you can do it for 5 people, but you cannot do it for 100 people. You cannot do it like every other hour or every day. Fourth point is that it should, and I think it's one of the most important points for microtransactions. As I said, that it's one-to-one. It should be low in latency. So what do I mean by low in latency? Let's say A and B want to perform microtransactions off-chain. A should be able to send microtransaction off-chain directly to B, rather than routing through other things or using some complex routing mechanism. And I'll sort of discuss that one of them in upcoming slides. So yeah, so what are the systems that already exist for performing microtransactions? The first one is state channels. So who all are aware about state channels? I guess, yeah, most of them. So I'll briefly explain what state channels are. So let's imagine A and B wanted to perform microtransactions. So what A and B can do is that they can deposit certain money on chain, that is create a state channel on chain, and then they can sort of send each other receipt off chain, which would be a replica of the state on chain, and then A and B can agree upon and then settle the state on chain. So like 3 steps. So you first open the state channel, exchange receipts, and then agree upon and settle the state on chain. So you can easily see that it's great for one-to-one exchange. So A and B can directly exchange the receipts off chain. It is low in latency. And one ideal property that state channels have is that it is secure. That means A and B have a guarantee, since they've already made a deposit on chain, they have a guarantee that they can actually redeem it for the underneath value on chain. But the problem with state channels is that you would require an on-chain setup for every new person that you want to do microtransactions with. So A and B have a state channel, but now A wants to pay A wants to pay C in microtransaction. So A will have to create a new state channel with C on chain. So that's per user that you're doing microtransaction with. Plus, we are thinking of applications that are small in value. So for example, I would be paying $5 over an hour or something like that. And locking up $5 in a state channel for an hour isn't capital efficient. And if you want to scale that linearly, it wouldn't be capital efficient at all. Because, I mean, once you're done paying the person, you wouldn't want to redeem it because the transaction fee would exceed the amount that you receive back. So it is not capital efficient. So there's an improvement on state channels, and we call them virtual state channels. Anyone familiar with virtual state channels? Okay, so virtual state channels are, so they follow the properties of state channels, but the special property that they have is that they eliminate the need of interacting on-chain for every new person that you want to set up state channel with. So the way it works is that you've got A, B, and C, and let's imagine B as the intermediary. So A has a state channel on-chain with B, and C has a state channel on-chain with B, and through B, A and C can set up a virtual state channel. That means they do not have to interact on-chain to actually have a state channel. And that's good, right? So you don't have to actually set up state channel for every new person that you want to pay in microtransactions. And it follows the properties of state channels. That means it is low in latency. It is secure. So A and C have a guarantee that once they settle the virtual state channel with B, they would be able to redeem it for some value that is underneath the receipt that is shared. But the bad part about virtual state channel is the intermediary, that is B. So there's a huge amount of reliance upon the intermediary. So if tomorrow B turns out dishonest and stops cooperating, then it would be really expensive for A and C to settle all their amounts on chain. So for example, let's say A, B, and C, now they've got many virtual state channels. There are many people connected to B as the intermediary. It would be very expensive for each and every person to actually settle their virtual state channel on-chain without the cooperation of the intermediary, that is B in this case. So it's very expensive. And this could easily turn into a situation where B might ask for transfer of certain amount of money to their account if others want to actually settle with it. So it could easily turn into an extortion case. The second point is that intermediary needs a huge amount of capital. So what do I mean by this? So when A and C set up a virtual state channel, B is representing C B is representing C in this case, and B is also representing A in this case. So the amount of capital that B needs is the amount of capital A and C put in. And you can imagine that if there are several people connected to B as the intermediary, which would be the case because B is it's sort of a hub network where B is the center, B would need the capital that is required by each and every user. And that's a huge amount of capital upfront, which is why intermediary needs huge capital. So we have another thing that is Lightning Network. So how many people are aware about Lightning Networks? One of the oldest ways of performing microtransactions off chain, right? So what is a Lightning Network? What is a Lightning Network? So basically, in Lightning Network, you upgrade yourself from L1 to L2. And L2 is the network on which you perform transactions. So the way you do is that you set up a state channel or a multi-sig contract with one of the L2 nodes, and then you upgrade yourself to the L2 node, L2 layer 2 network, and then you perform transactions. So it follows the properties of state channels, that it is off-chain. It doesn't require per interaction setup. So for example, I want to send transaction to someone else on the network. So I can route through the network and send them a transaction rather than have a direct channel with them. So it doesn't require per interaction setup. And following from state channels, it is secure. But the problem with Lightning Network is the time complexity for the routing protocol. So what do I mean by that? Let's say the Lightning Network has n nodes on the network, and A needs to send a transaction to B, and they do not have a direct channel set up between them. So what would happen is that in the worst case, it would take log n hops from different nodes for the transaction to actually go from A to B. And that is really bad for situations where you want one-to-one interaction, like it was in state channels. And I said that it is very bad for low latency, because log n is not good for low latency transfers. Plus, I believe that routing protocol adds unnecessary complexity to the problem that we are trying to solve over here, that is microtransactions. And the third thing is that given the nodes on the Lightning Network are not altruistic, they would charge fee for every hop that you do. So the more the hop that you have, the greater the amount that you will pay in fee for the transaction to be routed. And that's bad for microtransactions, right? You're routing 1 cent or, let's say 1 USD or something like that. And if there are many hops, then you would exhaust some amount of the money that you're routing in fee. So yeah, these are the problems with Lightning Network. And there's something called probabilistic payments. Anyone heard about probabilistic payments? Right, so the way it works is that, let's say we have A and B. B would set up a rate. Let's say in this case, B would set up a rate that they want to receive 1 ETH every 5 minutes. So what would happen is that A would send receipts constantly during 5 minutes. A would constantly stream receipts to B, but only one of those receipts would be valid. So that means only one of those receipts can be redeemed for value on chain. So the way it works is that A would constantly send the receipt to B, and all the receipts are invalid except one of them. So, and which is why we call them probabilistic payments. And the key over is that neither B nor A can actually game the system. So the way it works is that neither of them can actually change the probability by which B would receive a valid receipt. The point is that it is low latency because A is paying B off-chain directly, and it is off-chain. But as you can imagine, as I said before, that A continuously streams the receipt to B for this to work out. It only works for long continuous streams of payments. So you cannot do one-off microtransaction payments. The second point is that probabilistic payments are either secure or they do not require on-chain setup per user. So what happens is that in order for A to pay B, A needs to first deposit balance on-chain, and then only they can pay in microtransactions off-chain. So now if A wants to pay C as well, they would use the same balance pool to pay C. But what would happen in this case is that A can keep paying different people without guaranteeing that they can redeem it for value on chain. And that would mean that it is not secure. You can make it secure by having A commit certain amount of balance for every user that they are paying off chain. and that would require per user interaction. So that means it is either secure or it does not require any on-chain setup per user. So we've got these 4 systems that they already exist, and I would be introducing to Scaled. So what is Scaled? So Scaled is a project that I've been working on for past 2 months, and it's an off-chain microtransaction system. And the good thing about Scaled is that it is built on top of L2s. That means it actually leverages the fact that the execution cost on L2s is very cheap, and trades it off and uses that fact to actually reduce the amount of data that needs to be posted in transaction call data on chain. And that is how it minimizes the amount of fee that you need to pay for microtransaction settlement. Before I move on further, I would mention that Scale does not fit into all the ideal properties of microtransactions, and I will be talking about how to improve that in future right after this. So how does it work? Let's say B wants to pay in microtransaction to A. So what would happen is that B would first make a deposit on chain, and B would also make a security deposit on chain. And then A and B would share a receipt off chain, and the receipt is time logged as well as unidirectional. What do I mean by unidirectional? That means that using the receipt, only B can pay A in microtransaction. It cannot go the other way around. And then the receipt also records how much B owes A. And then after some time, after A thinks that they've received enough amount from B in microtransactions, A can redeem the receipt on chain for the value that it contains. That is how much B owes A. So the receipt somewhat looks like this. So you've got A's address, B's address. So A is the one who's receiving the payment off chain, B is the one who's paying. In this case, since the receipt is unidirectional, you only need B's signature. You do not need A's signature, right? Because they're the one who are receiving the payment. And B is the one who's paying, which is why we only need B's signature. Amount is how much B owes A. Expires by is the time after which the receipt is no more valid. And the sequence number records the number of the receipt. So for example, A and B share a receipt, after which A settle it on chain. But like if A and B want to share another receipt, they would have to increment the sequence number by 1, and that would be the latest receipt. So that sequence number is actually used for tracking the latest receipt that is shared between A and B. So when you actually add all these bytes, you get 201 bytes, and that's a huge amount of call data to be posted on chain. And you would notice that, and in subsequent slides, we'll be actually improving upon how much amount of data. We'll be actually optimizing the amount of data that is needed per receipt that should be posted on chain for microtransactions. So you can imagine a scenario where you've got A that is receiving unidirectional micropayments from B, B1, B2, and the same thing goes for A1. So you can sort of imagine that you've got A who's receiving microtransactions from several people, and then they take all these receipts, which are from a microtransaction, and then post them on chain together. And together is a key over here, because that's where we actually optimize data that is needed per receipt. So why do we make it together? Why does A needs to aggregate all the receipts that they have received from B, B1, B2, and then post them together under one transaction on chain? Because in that case, we can actually benefit from BLS signature aggregation. So what happens is that in BLS signature aggregation, you can aggregate different signatures into one aggregated signature and then post that on chain. So we actually go from every receipt having every receipt having the field of B signature, only one signature, and there is no need of including signature for every receipt. So we've already removed 32 bytes per receipt that needs to be posted on chain. But turns out that the moment we actually take many receipts and post them on chain, we can perform a lot more optimizations in terms of data. So the first one is that, first one is very simple. So we can actually replace every user's index, every user's address with an index. So an index could be in 8 bytes, that would be 2 to the power 64 minus 1 users, and that there are many, and that is a lot of users. So we actually replace A address with A index and B address with B index. So now we refer to users using their index rather than referring to them using their address. The second thing is also simple, that we reduce the data. We reduce the data by reducing the amount of bytes needed for amount. So we go from 32 bytes for the amount field to 16 bytes. And the point in this case is that you actually don't need 32 bytes for the amount, and you can actually, if you want to match YASI to transfer, something like that, you can directly multiply it on chain, so you don't need that. The third point is that you can remove expires by field and replace it on chain by an epoch. So you can sort of set up an epoch field that is like every week or an every 2 week, and every receipt needs to expire within an epoch. So rather than having expires by which determines the exact time when the receipt would expire, you replace it by an epoch. So you don't need the expire by field, you only post the receipts that would expire within that epoch. And then we can adjust the epoch depending on the usage from 1 week to 1 day or within an hour, doesn't matter. We can also remove the sequence number and reproduce it on chain. Since I said that sequence number tracks the latest receipt that A and B share, and every new receipt would increment the number by 1. What we can do that we can actually track the number on chain, and every receipt that you receive from A, B, you can sort of increment the number and check whether it is valid or not, and you don't need to include it per receipt. And another optimization that you can do, if you restrict that only A can post their receipts on chain, you can actually you can remove A's index and include it just once. So you don't need to include A's index in every receipt. So finally, after all these optimizations, we come down to something like this. So every receipt only needs B's index and the amount, and we need one aggregated signature and A index. So we went down from 201 bytes per receipt over here to 24 bytes per receipt. And that's a huge amount of saving. And we were only able to do it by having few assumptions about that only A can post the data, and A will have to aggregate many receipts into one particular transaction. And these are the results. So if A is aggregating 10 receipts, they would have to pay 0.5 USD if you actually take conversion rate 3,000 USD per ETH. So for 10 receipts, the total cost is 0.85 USD, and for 100 receipts, the total cost is 3.7 USD, which is a good amount of optimization. And if you want to dive deeper into scaled contracts and documentation and stuff, you can scan the QR code and have a look at it. So, as I said before, scaled is not ideal because it is not secure. As I said that B deposits certain amount on chain, and then they can actually send payments to A, A1, A2, A3 off chain. The point is that B doesn't guarantee that all the receipts can be redeemed on chain for the specific value, because they haven't committed to every specific user, because every specific user is sharing the same pool of balance. It's similar to probabilistic payments in terms of security. The second point is gas cost. So since we are verifying aggregated signature, that requires pairing. And since every receipt is a different message, that would require n+1 pairings operations on chain. And if there is a limit of, if there's a limit on gas units that can be used per transaction, that would limit the number of receipts that you can post on-chain at once. So that's a limit in case of gas cost. Okay, so where are we headed in terms of microtransactions? So this is sort of a speculative thing, and I still have to research a bit more on this. But I can sort of say that I think we're headed to state channels, because state channels are one-to-one. They are secure, which others don't, which is a property that other systems don't have. Plus, state channels are easy, and they can represent arbitrary state. And these are the good things about state channels. And if we are able to make it very cheap in terms of opening and settling many state channels at once, then we would overcome the problem of locking up capital per channel, because you can settle one very easily and very cheaply. And we would also overcome the problem of having to require on-chain interaction per user, because you can open a state channel and settle a state channel very easily and cheaply on-chain. So how can we do that? So the first way we can achieve that is by having BLS signature aggregation. So what you can do is that you can actually aggregate several state channels, settlement or opening into one, aggregate their signatures and post them on chain, and by that you would actually save huge amount of call data. And this is what we did in Scaled. And hopefully in future the data cost reduces, so that would make it much cheaper as well. Plus, the good thing about BLS signature aggregation is that it is easier to implement. You can implement it right now. The second part is that we can use ZK proofs plus accumulation scheme to actually achieve this. So what you can do is that you can create a proof of opening or settling a state channel, and then aggregate all the proofs into one aggregated proof and then post them on chain. I'm not sure how beneficial it would be as compared to BLS signature in terms of call data, but I think that if you actually take only the balance delta, that is the balance change of every user as the public input, then you can actually optimize it further and reduce the amount of call data that needs to be posted on chain. But I'm still sort of fuzzy on how to achieve that. So we can reduce I believe that we can reduce the call data that needs to be posted using ZK proofs much more than using BLS signature. But the hard part about ZK proofs and accumulation scheme is that it is very hard to implement. The prover time is a lot, and there are a lot of things that can go wrong in ZK proof. It's very hard to audit. The circuits are really hard to audit, and that in accumulation means that it is really hard to get it right. So thank you. So if you're interested in learning more about us, that is PSC, that is Privacy and Scaling Exploration Group, or joining us, you can scan the QR code or visit our site at appliedzkp.org. And if you want to get in touch with me, my Twitter handle is Janmajaya_Mall, or if you want to get in touch on GitHub, I'm not sure you can chat on GitHub, but yeah, you can visit my GitHub and check it out. Thank you.